Welcome back. Lecture 7 is where we are today. The broadcast actually, and I don't know if you're aware of the fact that this is broadcast kind of a week later for those of you in this classroom on Raleigh Cable Channel 18. So they started last night. I thought it was kind of unique when I walked in the house. My wife is sitting there in the couch in the living room watching the broadcast. I mean, I'm sure there's probably something better to watch. I believe it's 5 to 6 a.m. and 5 to 6 p.m. or when the lectures run, but they're a week behind us. So I figured she'd have a pad of paper and, she'd be writing stuff down. Why don't you wear this? Why don't you do this? Speak louder. So actually she had one critique, and I'll try to honor that. Somebody on the first day of class said, would you not write cursive and would you print? That was you. Okay. So I've tried to do more of that, haven't I? So I'm trying to, but when I kind of write fast, I'll write cursive, and sometimes it's not legible. So, and I realize that. But I was ready for this big critique because she is a videographer. She does that for a living. She writes scripts and films video and does commercials and public service announcements. And so I thought this big long list of things, come on, you got to do better than that. So it wasn't bad. So the good thing about it is if you miss this class, you can see it later, but it's a week later on cable TV. Yes, sir.
Is that
Kelly.
exactly 1 week?
Yes. Right now it's exactly 1 week because we started on Wednesday, and yesterday, being Wednesday, was their first broadcast on Raleigh Cable. So.
Is it like all the days combined? Like, or is it just one
It's
episode?
one day. I mean, they'll show a 50-minute lecture, and then the next day they'll show the next lecture.
Oh, the next day, like
Yes.
not the next week.
Yeah.
So it's
Yeah.
on every single day.
It is, yeah. And people
what
all over Raleigh are lamenting that fact. That, especially me, on at the dinner hour, not exactly, very good for digestion. But they're hopefully tuning in. I have 10 people right now taking this course on cable TV. And then I think I told you that it'll roll to DVD after this semester, and we'll have people literally all over the world taking this course. So it'll be used. Okay, we left off yesterday with kind of the basics of exponential functions. I don't think we did y equals e to the x. I think we did y equals 2 to the x. We graphed that. We also graphed y equals 2 to the negative x. E to the x is very similar to 2 to the x, kind of a strange base, e. E is a number. Probably E would be my guess because the Swiss mathematician Euler, E-U-L-E-R, probably did more to kind of put stuff together surrounding this strange number than anyone else in antiquity, so probably called E due to Leonard Euler. Before we come back and graph this, I'm going to need some calculator help here. If we take a limit of 1 plus 1 over n to the n power, as n approaches infinity, let's take a look at what that looks like. That is, in fact, one of the ways of defining what e is, this number e. It doesn't seem right when you first look at it. 1 plus 1 over n, well, if n gets huge, what's 1 over 600 trillion? It's very, very small, practically 0. So this is 1 plus practically 0, which you think is really, really close to 1. And 1 to some huge power is simply 1. But because it's a little bit larger than 1 and we're raising it to some huge power, it actually does converge on this number that we know as e. Let's take a little, if some of you have a calculator, this isn't very large, but let's say n is 100. What would 1 plus 1 over 100, that quantity raised to the 100th power, what would that be? Anybody?
2.7048.
2.7048?
Yeah.
Anybody get the same? Okay. That's pretty close already, isn't it? And we're not very close to infinity. I mean, 100 is large, but it's not that large. So what happens if we let n equal 10,000? Again, still large, but not nearly as large as it's going to be.
2.7181.
2.7181. Okay? That's pretty close, right? In fact, it's accurate to at least 3 decimal places. So as n approaches infinity, this thing is actually equal to the number e. That's one of the ways that you can come up with this value e. It is the natural exponential function. So its counterpart, which we're going to deal with in a little bit, is the natural logarithmic function. You're probably used to that, natural logs, but you're probably not used to calling this the natural exponential function, but it is because it's base e. So that's somewhat of a strange number, but it does kind of rear its head in mathematics in a lot of different situations. So it's common, even though it's kind of a strange number. So if we were to graph y equals e to the x, I'll need some help here too. What is e to the negative second? That's 1 over e squared, right? What would that be? Point 0.135. Thank you. What is e to the negative first, which is 1 over e?
0.3668.
0.368. Okay, and these are not exact, but they're pretty good approximations. E to the 0, we can do this one exactly. That would be 1. E to the 1 is the e to the first is just e.
0.79.
And e squared,
7.389.
thank you.
Can you find out those values without a calculator?
E to the 0, yes.
No. Yeah.
E to the 1, yes. Probably not. Okay. Even if you had an arithmetic calculator, the 4-function calculator, you could probably, using what you know e to be, 2.718, you could come up with them. Mm-hmm. But as far as just without any calculator at all, that's going to be kind of difficult. So at negative 2, we're way down here. Negative 1, we're here. This ought to look familiar, by the way. A little different shape. So it gets pretty steep over here. So it is asymptotic to the x-axis. You're never going to get 0 for a y value here. As small as x might be, x could be negative 10,000. You're still not going to get 0. But it does get pretty darn steep over here, and that's a characteristic of this curve, kind of a unique characteristic of this curve, the natural exponential function, is its slope right here. And I don't know how accurate my graph looks. I don't think it's too bad. The slope at that point is, any guesses?
45 degrees.
Okay. So if it's a 45-degree line, its slope would be 1. So the slope at that point, at the point 0, 1. And we'll validate some things about slope when we start talking about derivatives. But that's one unique characteristic of this function, is its slope.
Sorry.
There is 1. Yes,
Isn't
Catherine?
the derivative of e to the x just e to the x?
Yes, it is.
Okay.
Okay? And some of you, now that sounds strange. I can see that expression on your faces, some of you. First of all, the derivative, when somebody mentions derivative, think slope. Okay? That's what a derivative is. That's our first meaning that we'll attribute to it. We're not there yet. We're getting there. but the slope is the kind of the derivative at any certain point, the instantaneous rate of change, if you want to call it that. So that is a very unique thing about this function that we'll visit later, is that the derivative of e to the x is itself e to the x. So if you want to know, and I'll repeat this later, you're not responsible for it right now. If you want to know the slope at any point on this curve, pay attention to the y value, because the y value is e to the x. So the y value is the slope on this curve. So what's the slope right here? The slope is 2.718. What's the slope right here? The slope is 7.389. So that's very convenient about this curve. Okay, what are curves like this used for? We looked at a couple of curves yesterday. 2 to the x had this same basic shape. Not quite so steep as this one. 2 to the negative x was the mirror image of that on the other side of the y-axis. Typically, these are used for growth functions, and these are used for decay functions. You've probably used that in another math class prior to this one, which is, I think, valuable, that you have probably looked at an equation in this form. And there have been numbers occupying, so maybe this is 100 e to the 0.045 t. Okay, we've got y in terms of t. This is a growth function because it's e to a positive power. In like fashion, if you have something like this, I'm just making up some coefficients now. If you have a negative in that exponent, it's growing negatively, while something doesn't grow negatively, it decays. So these are used in mathematical modeling, the positive exponent for growth and the negative exponent for decay. Depending on the problem, we may or may not need this portion of the graph. If t is time, we're not going to back the clock up, so to speak, so we'll start at t equals 0 and we'll look at the rest of the graph from there. So growth and decay, population growth, growth of bacteria in a culture, decay, a radioactive substance that they're going to put in a lot right down the street from where you live. You might want to pay attention to its decay factor. How long is it going to be there? What's its half-life? Is it, does it decay very rapidly, or does it have a half-life of, 360 years? I don't think I want that in the lot down the street from my house because it's going to be there for a long time. But if its decay rate is pretty quickly, I'm not going to worry about it if it's not too volatile. A couple of quick functions, and we'll leave this and move to the next section. We will revisit these, but I'd like to at least get a start with them today. Y equals 1/2 e to the x. And y equals 1/2 e to the negative x. And then there are certain combinations of these that actually become another function. 1/2 e to the x, that ought to be, I'm going to put them together. That ought to be just e to the x. Every y value is half of what it was normally, right? So that set of values we just plotted, where it was 7.389, it's now going to be half of that. Where it was 1, it's now going to be half of that. So the basic shape of that is very similar, but a little bit flattened out, not quite as steep. So that's this one. 1/2 e to the negative x, put that in a different color. Because it's e to the negative x, we're going to have the mirror image of that on the other side of the y-axis, so it's going to be over here and over here.
Sorry.
There are some functions in mathematics that are combinations of these two. They call them, they look like trigonometric names, but they're really not trig at all. They just have some properties that are similar to trig. Have you worked with that function in another math class? Hyperbolic cosine. Have you seen that key on your calculator? Looks like a cosine with an H on it. So maybe the first time for most of you that you've seen this function. Or the other function is hyperbolic sine. So they have that look like trigonometry, but they're really not trigonometry. They're exponential in nature. They they have some properties like trig. If you add these two, the red dotted line function and the blue dotted line function, if you add them up, you get, it kind of looks like a parabola. It's not a parabola. It's called a hyperbolic cosine. So those are the same. That's the definition of hyperbolic cosine. We'll revisit that later in this course. Actually, let me come back and do, it's plus, so it doesn't matter. I'm going to do the positive one first and the negative one second, because over here we want the positive one first and the negative one second. So there's a definition of hyperbolic sine. This is relatively new information for me. This is sometimes called the shine function. I've heard it called sinh before, but it's a new word, shine. Hyperbolic sine, shine, and this is called the cosine, okay, or hyperbolic cosine.
Aren't those the exact same thing? No one's.
This is plus, and this is minus. So they are very similar, and in fact, that similarity is what causes them to possess some properties that are similar to trigonometry. I know some of you have had some trig, and you know the derivative of sine is cosine. Okay, very similar interrelationship here, which we will revisit later.
Okay.
But I'll just sketch one of them. If you were to add these two curves up, you can actually add them up on the graph. You can take the y value here and add it to the y value here, and you get a value up here. You can actually just do addition of ordinates and plot points that way. The hyperbolic cosine has this kind of shape. So when I said earlier it's kind of parabolic, it's not a parabola. It is this function right here. So if you were to plot points using the blue graph and the red graph, you would actually, at individual x values, you would get a shape that looks like this, hyperbolic cosine. So we're not going to do anything with them now except point out that these are exponentially based, and we will revisit them later.
What would you show on the top? That's cosine, or is that sine?
This, the green one, is the sum of these two. So that's the cosine or hyperbolic cosine. And I'll address later why it's called hyperbolic, but that right now we don't need that. All right, advance to section 6 in the text. Inverse functions and logarithms. So we just did exponentials. If you take the inverse of an exponential, you get a logarithmic function. Very valuable in mathematics. Why would we need logs, or in general, when would we need the inverse of an original function? Functions are valuable, so you have this function, and you plug in numbers, f of 1, f of 2, and you plug it into the function, and it spits out the corresponding second element that's paired with it. So if we want f of 1, or f of 8, or anything like that, we can use the original function. It's wonderful for that. Kind of plug and chug. Let's suppose that we want to know the f of x equals 81. So we know the y value. We want to know what x value generates that. So now we're going to try to reverse what's going on in the function. We want the inverse, or the f of something is 243. What is that something? So inverses do have value in mathematics. Depending on the original function and how complicated its inverse happens to be. It's not necessarily more complex than the original, but it's another function. So if we want to find the inverse, first of all, we want to start with a certain kind of function so that its inverse is also a function. So we want to begin with a function that is 1-to-1. What is a 1-to-1 function? You've had it before. Every one of you have had it before.
So each x value is assigned to one specific y value.
Okay, each x is assigned a unique y. That makes it a function. Now what makes it a 1-to-1 function?
And every y is assigned a specific x.
That's correct. Every y is also assigned a unique x. So not only does it pass the vertical line test, that makes it a function, it also passes the horizontal line test. So every x is assigned a unique y, every y is assigned a unique x. So it passes the vertical line test, and it also passes a horizontal line test. If it doesn't, we need to do something, delete part of it, restricted domain, I like that better than delete part of it, so that it is 1-to-1, and we can find the inverse, which is the function. Blair.
If a function doesn't pass the horizontal line test, does that mean its inverse will not pass the vertical line test?
That's exactly right. And we want the inverse, in most cases, to be a function. So that's why we want to restrict the original so that it's 1-to-1 to guarantee that that will happen. So if we begin with a function that's 1-to-1, we want to switch or interchange x and y, and normally we want to solve for y. So you know that. You've done that before, but the restricting of the domain to make sure that it's 1-to-1 is something we want to make sure that we do. So if we start with, this is just notation, if we start with y equals some f of x, and we want to find its inverse, then we want to end up with the inverse function. So that notation we've already used once in here, just reiterating that it's not f to the negative first. It is not that. It's a notation that means f inverse. So y equals 2 to the x. We've used that already. We know what it looks like. It's one of those, or could be one of those exponential growth type functions. We want to find the inverse. We will interchange x and y. Either solve for y or kind of describe what y is. That's your choice. I'd rather at this point just say, what is y? Y is the power that you would raise 2 to get x. Okay, that's a statement in the English language. What's a mathematical statement that says the same thing I just said? y is the power that you would raise to get x. Y is the power. What's another word for power? Exponent, or another word. Feel like a game show host here. Logarithm. Logarithm means exponent. So y is the power that you would raise to, where do I put the 2?
The bottom.
Okay, subscript it because that's the base. Y is the power that you would raise to, well, there's only one other place left, and that's right here, right, for the argument. So this thing and this thing, and hopefully they look like they're inverses, right? These are inverses of one another. Y equals base 2 raised to the x, and y equals log to the base 2 of x, completely interchanging the roles of x and y. Is this, I should have addressed this before, and I made a mistake by not doing that. Is that 1-to-1?
Yes.
It is. It passes the vertical line test. It also passes the horizontal line test, 1-to-1. So this would also be a function. So what does 2 to the x look like? It looks something like that. Visually, in the plane, how would log to the base 2 of x, what would it look like?
It's just the same thing flipped over the y.
Okay, not the y-axis, but
X.
not the x-axis,
The origin.
not the origin. We'll get there. We'll keep naming things. It's okay. The guesses are wonderful.
Isn't it the
It's like y equals x.
The line y equals x. Okay, so if we'll take this line, which is the line y equals x, and we'll take the mirror image of this, like we fold up the coordinate plane, we crease it right there and fold it up, then the two functions ought to coincide. So if that is the case, and you can flip points if you want to and kind of do individual points, 0, 1 becomes 1, 0, right? The point 1, 2 becomes 2, 1. So that ought to be log to the base 2 of x. So if you folded this thing up on this dotted line, put it together, these two graphs should coincide. So that's y equals log to the base 2 of x, roughly. I mean, it's a sketch. And that roughly is what y equals 2 to the x look like. Anytime you have points, just interchange x and y, and you can get started with the graph if it's not exactly obvious where to go with that graph. Okay, let's take y equals e to the x. And find the inverse. And let's call this, actually let's use both notations. Y equals e to the x, or f of x equals e to the x, kind of the same thing. What's the inverse of the natural exponential function?
Natural log.
The natural logarithmic function. Those are inverse operations of one another. So we could switch x and y. What is y? Y is the power that you would raise e to get x. Is that correct? Hopefully that sounds right and looks right, although it looks a little different because we normally don't write log to the base e, we write ln, right, natural log. But they mean the same. Natural log is a base e logarithm. So our inverse that's our original function, which again, I made the same mistake. Is e to the x 1-to-1? Yes, it is. Therefore, we can find its inverse and expect it to be a function. F inverse is natural log of x. We haven't done this yet. What happens when you compose a function with its inverse?
Which is
Chandler, I think you said it.
1?
No.
X?
X.
Yeah, X.
You get what you start with. So if you start with x and you go through a composition of functions that basically inverts the role of x and y, you ought to be back kind of where you started. So this means the f of the f inverse it ought to be back where you started. Let's validate it in this case that it is true. So if we did f of the f inverse, what's the f inverse?
ln.
ln, natural log of x. And what would we do to take the f of that?
Raise the e. Raise
E
the
to that
ln.
power, right? To this whole thing. The f function is e to some variable power. What variable power? This. I don't know if that looks like a self-answering question to you, but it does to me. What is this? That's the power you would raise e to get x. You turn right around and raise e to the power that you would raise e to get x. For goodness sakes, you ought to get x. What's the name of your brother whose name is Bob? Well, I believe it's Bob, isn't it? That's the same thing. Exactly the same thing. It's a self-answering question. This power is the power that you would raise e to get x, and you turn right around and raise e to that power, you better get x. And we should be able to compose them the other way. Before that, let's say that we had a set of points, and see if this makes sense, that whatever we start with, we ought to end with. Let's say that in f inverse, we start with x, which is what we're supposed to do first here, right? And it sends us to some value. I'll just put a Greek letter, alpha. If x comma alpha is in f inverse, what point is in f? Alpha comma x. Is that true?
Yes.
That's the way they work. You flip-flop the x and y value. So what do we do here? Well, we start in the f inverse. X kind of sends us to alpha, and now we go to the f function, and alpha sends us back to x. Doesn't it kind of make sense that what we start with, we should also finish with? There's some intermediate value. X sends us to something. That something sends us back to x. So it doesn't really matter what this is. That's kind of the x got sent to that in the inverse. Flip them around. That value sends us back to x on the other function. So there could be lots of other points. But that's how it works, that what you start with, you ought to end with. So can we compose them the other way and expect to get the same result? We should. Composition of functions, is that okay? Everybody comfortable with composing functions? And we're just composing two. You could take the f of the g of the h of the j. Right now we're taking two functions in a composition. So with our functions, what's the inside function? What is the f of x?
E to the x.
Okay, back up here. F of x is e to the x. And if we take that whole thing and place it in the position of the variable in the f inverse function, what do we have?
Natural log.
Natural log of e to the x. To me, that's a self-answering question. What's the natural log of e to the x? It's x, right? When you take the natural log of something, you're looking for the power that you raise e to get that. What power do you raise e to get e to the x? You raise e to the x to get e to the x. So when you compose a function and its inverse like this, you ought to be back where you started. When you compose a function and its inverse like this, you ought to be back where you started. We start with x, we end with x. This is probably overkill here with this problem, but I want to make sure that we kind of are all on the same page when we're dealing with natural logs. Let's suppose that we don't have some arbitrary x value, but we have a number here. When you're looking for the natural log of 2, aren't you looking for the power that you would raise e to get 2? Is that correct?
Yes.
So when you punch the buttons on your calculator for natural log of 2, somebody do that, 0.693 147, okay, we'll call it 1. That's an approximation that your calculator gives you. You might kind of wonder how your calculator is not very smart. It doesn't know natural logs. It does this some iterative way, which you learn as part of Calc 2, a Taylor series and a Maclaurin series. But so it kicks out this value. What does it spit out for us? It spits out the value that is, in fact, the power that you would raise e to get 2. So if you're looking for the natural log of something, you're looking for the power that you would raise e to get that something. So if you'll keep that in mind about natural log, it really can make natural log problems a whole lot easier. Now, you're not going to get exactly 2 on your calculator here, but it's going to be very, very, very close to 2 because this is an approximation, not an exact value. Let's suppose that we wanted to solve this problem. Well, this particular model. Say we had a function, it's a kind of a standard exponential growth and decay type problem. And we want to know, we know the starting value for y, we know a future value for y. What we don't know is how long it takes to get there from the starting value to the future value. So let's say we have some numbers. For the future value or final value, we're going to put in 500. For the initial value, let's put in 100. And for this growth rate, we put in 0.15. Don't we need logs to solve that problem? Aren't we kind of stuck without logs? So let's go through a procedure. How would you solve for t?
Divide by 100.
Divide by 100.
Take natural log.
Take the
both
natural
sides.
log.
There we go. Okay, we're kind of forced at that point, right? So 5 equals e to the 0.15t. Without logs, or most specifically in this problem, without natural logs, we're without a weapon. We need to solve for t, which is in the exponent position. So we'll take the natural log of both sides. This is where I think that comes in handy. This simple statement right up here. What does it mean for the natural log of 2? That's the power that you would raise e to get 2. What power would we raise e to the, let me rephrase that. What power would we raise e to get e to the 0.15t? 0.15t. So we end up with natural log 5 equals 0.15t. Others of you might be more comfortable with taking this exponent and bringing it out in front. Isn't that kind of what we end up doing anyway, right? And then you have times the natural log of e, which is 1. Now we can solve for t, but to solve for t, when t was in the exponent position, we were kind of forced to use logarithms. So if we started with 100 something and we ended with 500 of that same quantity, we knew the growth rate, how long would it take? This is how long it would take. Whatever the natural log of 5 divided by 0.15, that's how long it would take at that growth rate.
Is this all you ask us to do on tests? We can't use calculators?
You can use calculators on tests.
What about graph calculators?
You can use graphing calculators on tests, but if the problem asks you to graph, then the graphing mode or the graphics mode is kind of off limits for that problem. But even if you had just a scientific calculator, if it does exponentials and logs and trig, and it doesn't graph, you can use that, and that'll work. Did somebody run that through?
Yeah, 10.7295.
10.7 roughly?
Yeah.
So depending on what the units are for t, it could be 10.7 days or 10.7 months or 10.7 years. We don't know that. I just made up a problem. Blair, you had a question.
What calculator will we use most as we keep progressing through calculus, like past this stage?
I think graphing calculators are valuable. I'll be honest with you. I own one, but I hardly ever use it. But I use the heck out of a calculator that does exponentials and logarithms and trig.
It's nice to have all that on the screen too.
Yeah.
Is that
But calculators that are off limits, and I think I addressed this the first day, are calculators that do calculus. If the calculator does derivatives, like a TI 89 or 92, they're wonderful machines. I'm not trying to say that Texas Instruments is a bad company because they made these. They're wonderful, but they give you an unfair advantage because somebody that doesn't have that calculator, they don't have the ability to check their work. Hopefully you would not do your work with that, but I mean, you could check your work with that. So if your calculator does calculus, it's off limits. So if you have a TI 89 or a 92 or another like an 84 plus that has a subroutine that does symbolic manipulation, it does derivatives or integrals, then you need to find another calculator to use on tests, because that's unfair. I'd rather know if you know calculus than if your machine knows calculus. Let's get one where we have to restrict the domain before we stop this topic. Let's suppose that f of x is x squared plus 2, not 1-to-1. Can you picture that? Parabola that opens up 2 units above the origin. Not 1-to-1 because it passes the vertical line test but does not pass the horizontal line test. So what could we do to our original function before we go ahead and switch x and y and go about finding the inverse? Restrict the domain. And just basically, in this case, get rid of half of it, right? Okay, so let's say that we want to use this function, but we don't want it all. We want to start with 0 and everything to the right. So there's our domain. So of this original f of x that's not 1-to-1, we only want that part of it. Now it is 1-to-1, passes the vertical line test, passes the horizontal line test. So let's find the inverse. So we would switch x and y. Solve for y. Somebody take that over. Okay. So you put your 2 steps together, which is fine. So you subtracted 2 from both sides. And then take the square root of both sides. Now, when we take the square root, initially account for both possibilities. Do we want both positive and negative square roots here? No, we really just want the positive. We want the upper half parabola. We don't want the lower half parabola. So for f inverse, we want the principal square root only. Which would look something like that, right?
So if we wanted the negative, or if we were to take the negative, that means that we were restricting the domain on the left side?
That's exactly right. So for the piece that we wanted, 0 to positive infinity, we want the principal square root down here. I don't know if you can see that visually, but if you would take that line y equals x, there should be a natural symmetry there since these are inverses of each other. Do those look like inverses to you? Sometimes you can check them when you're done. What's the first thing you do to x here when you're plugging a number in? Square it. What's the last thing you do to the variable quantity down here? Take the square root. Are those inverse sounding things to you? I hope. What's the second thing you do to the variable quantity up here? Add 2. What's the first thing you do to the variable quantity here? Subtract 2. Those sound like inverse things. So you not only do the opposite operation, but you do them in the opposite order. And those should look like and sound like inverse functions. Just a few seconds, we can finish this section. So if we know what e to the x looks like, we can visually get our natural log function. So e to the x is up here. Natural log is something that looks like this. What would this look like? What would we do to our old friend here, or to the right 2 units? Pick it up, slide it over 2 units, slap it back down. We've got the new function, right? So you can do it point by point if you want to. I would probably take this point right here, pick it up 2 units, and slap it down. I'd also pick up the asymptote, slide it over 2 units, and our new graph would look something like this, right?
Yes.
And what would this look like? And we'll be done today. Up 5 units and to the right 2 units. So here's our right 2. Here's our up 5. So we would take this picture right here, the dotted line picture, move every point up 5 units, and we've got it. Does that sound right? Okay, done for today. Have a nice long weekend, and I will see you after that holiday break.